And just very quickly, we defined a holomorphic function as something that has a derivative, a complex derivative, in that I have the familiar limit existing, but here now h is any complex number and the division is in the complex numbers. So okay, let's maybe go on in this direction a little bit further, and then let's do examples.
Sir, I guess you have to record or start the recording.
Excuse me. Yes, thank you.
Recording in progress.
Okay, so we defined a holomorphic function last time as something that has a complex derivative at every point in an open set. And then it is called holomorphic in that set. So this is a complex valued function defined on some part of the complex plane. And the definition of the complex derivative is exactly what you saw in your Real Analysis 1 course, except now both the numerator and denominator are complex numbers and the division is taken inside the field of complex numbers. Okay, and then, so we saw this fairly easy fact, which is that since this limit is supposed to exist, so we assume that the function f has a derivative at a certain point z0. Since this limit is supposed to exist, in particular, the limit will exist if I move along the real direction or if I move along the imaginary direction. And equating the answer that I got by these procedures, by both of these procedures, we got the Cauchy-Riemann conditions, which is that number 1 and number 2 must be equal, which gives me this star. And then I asked you to see that actually we can get a bit more, which is that if it's a complex differentiable function, then not only are these partial derivatives supposed to exist, and must satisfy these conditions, but actually the derivative in the sense of multivariable calculus must also exist. And then its Jacobian is the one that is given by Cauchy-Riemann. I mean, it must satisfy the Cauchy-Riemann condition. So this is a very, it's a useful little exercise because it will force you to revise what it means for the derivative of a multivariable function to exist as a linear operator. Okay, so please do this exercise. And I just want to say a few things here. Going further in this vein, remember we said earlier that if a function is holomorphic on an open set in the complex plane, then its derivative is also holomorphic. This is very different from what we saw for real numbers. So let's write this down. So let's write this way. K is equal to R or C, and derivative of a function f from U to K. U is open K at a point let's say P is the limit if the limit exists, of course, and this division isn't. Okay, so with this in so here is the contrast. If K is equal to R and A is equal to C. And U is some open set. So here and here we will say complex differentiable function. So real differentiable functions on an open set U. Now, so we have seen a hierarchy here, right? C1 functions, which is to say that a function is differentiable, but the derivative is also continuous. So here I have a strict inequality, right? And then I can go on, which is to say that this is twice differentiable functions. And then C2 functions. And so on and so forth, right? Until I finally get smooth functions, which is C infinity. That is infinitely differentiable. And then of course, every derivative also has to be continuous. All right, so everywhere I have a strict inequality. So the amazing thing over here is that this is all so this is all equal. And this should be straightforward to see from the quoted fact, which we have not proved by the way, right? That if a function f has a complex derivative, then f prime is also a differentiable function. But now it goes further.
Sir, in the hierarchy for real functions, shouldn't the inclusions be reversed?
Oh,
Like-
sorry. Yeah, sorry. Okay. Yes, thank you. So it's implications, right? So this is strictly subset of and strictly subset of. And now here I have real analytic functions. So what's an analytic function? Was this defined in the analysis 1 course?
I think so, sir. One with the power, like the power series converges.
Yeah, so what this means is that real analytic functions. So this means that for all P in U, there exists a neighborhood V of P such that if I write the power series such that for all x in V, I can write, so I have this Taylor series now, right? So this is sum from 0 to infinity, and this is just a one variable. So nth derivative of f at p is the point I used, divided by n factorial times x minus p to the n. And what needs to happen? This Taylor series actually converges and it is equal to f of x. And this is supposed to happen locally at every point. Okay. So this is what a real analytic function is. So I already sort of gave the game away, but was this, were you shown an example that a smooth function need not be real analytic?
If I'm not mistaken, I think it was e to the -1 over x or
So,
something along those lines.
yes, exactly. So these functions are important. However, for holomorphic functions, this does not happen. And that's the reason why you often see the word holomorphic and analytic used interchangeably. But that's because of a theorem, not because of definition. So recall a smooth function and this may seem like a special example, but you can play with this and you can do lots of other stuff. So what is the power series of this function? Around 0.
It's identically 0.
Yeah, because you see this function, the way it is made, it really just collapses. All of its derivatives at 0 are 0. So power series is identically 0. Check. I mean, including the value. And you can play with this function and you can do many things with this. You can make a step function. So there is only sort of one point, where something happens, but you can have this behavior happen at multiple times. You can make a step function by using this function appropriately. You can make bump functions out of this. So you can have a function that has compact support. That is, the values where it is non-zero are exactly in some open interval. And so the support of this, which by definition is the closure of the set where the function is non-zero, that is a compact set, etc. So a lot of wonderful stuff to be done. But this is real analysis. For complex number, for holomorphic functions, this does not happen. So this is just, so let me just say this is facts. All of which you will see in complex analysis. Okay, so yet another remark. We started the semester by defining non-linear spaces. So we can define a non-linear space where the underlying field is complex numbers. So recall the conditions. How many conditions were there in the definition of a non-linear space? There was the triangle inequality, and that really does not depend on, that really doesn't depend on the scalars, right? So where do the scalars come into play? I mean, what has to be rethought if we want to define a non-linear space where the scalars come from complex numbers? The homogeneity condition has to be rethought, right? So lambda v, so norm of lambda v is equal to, this is what we had, no? Regard absolute value of complex number lambda. Yeah, so I should really say the underlying field is complex numbers, but the norm is not a complex number. The norm is still continues to be a non-negative real number, which is 0 only for the 0 vector. So usual. And again, I can write various norms on finite dimensional complex vector space. But really, as far as topology is concerned, does it really matter? So suppose I take a complex normed linear space, a finite dimensional complex vector space, which is a normed linear space with complex numbers as scalars. In other words, this equality that I have written holds for all complex numbers lambda. And suppose I define the corresponding topology, right? By taking balls. Will I get any different topologies this way?
No, I think our proof of equivalence of norms holds for any finite dimensional or non-linear space.
That is true, but also notice one thing. If I make Cn to be a normed linear space, a complex normed linear space, then it's a vector by any complex scalar. In particular, I can multiply it by any real scalar. So an n-dimensional complex vector space is also a real vector. And what is its dimension as such?
2n?
2n, exactly. And now, so it's a perfectly good non-linear space, no? Still real non-linear space. So whatever norm I had, complex norm, if I just forget some of the conditions, namely that I'm allowed to, that this norm behaves well with respect to complex scalar multiplication. If I just apply it to real scalars, I still have a real non-linear space. And so I'm going to get a topology, which is perfectly, and I know that all norms on any real non-linear space are equivalent, which is much more than saying that they give me the same topology. But in particular, it gives me the same topology. So it really doesn't, as far as just topology is concerned, it doesn't matter. So let me just write this down. Is also a real so we get the same topology for all from complex norm as well. Okay, good. So let's see a couple of examples now. So examples. That is, we are going to leave our sort of not even a tour. It's just sort of a glimpse of complex analysis where we just said some things. But you should absolutely know the Cauchy-Riemann conditions, how they come about, and you should also do the exercise that I asked you to do. Okay, so let's do an example of Lagrange multipliers. Now, I gave you some examples in the last class, saying you should work them out. But I won't do any of them because anyway, they are worked out in Professor Pramat's notes, so you can see the examples. I'll do something else. And you can make up your own examples. So let's say f is equal to x square plus y square plus z square. Small variation. Minus 2x plus 4y. Find extrema of subject to, let's say, square plus y square plus z square less than or equal to. Okay, so let's do this. What do I have to do? So break this into, so what is the region over which I am maximizing geometrically?
The ball.
Yeah, right. So it's a closed ball. So both the interior of the ball as well as the boundary. This is a compact set. I have a continuous function. So I'm assured that there is going to be a global maximum as well as a global minimum. So break into two parts. Which is p equals x square plus y square plus z square less than 9, and the boundary of p. Okay, so in this part, what do I get? I do the usual thing. So I take the gradient. F prime has to be 0, right? I find critical points, but that means the gradient is 0. So what is the gradient? 2x, let me write it as a vector, 2x minus 2. I mean, this is just straight work. So 2z, and this is equal to 0 for critical points. So that gives what? What does it give? 1 minus 2, 0. And then I can calculate the value of the function on that, so that I will let you do. So this is 1. Yeah, so what do I do? Here's where Lagrange multipliers come into play. So what do I do over here? 2x minus 2, 2y plus 4, 2z. And what about this? So what is the condition? What does the Lagrange multiplier method tell us? If I want to find maxima or minima of a function subject to a constraint. So remember, the constraint over here is the constraint function is h, which is x square plus y square plus z square equal to 9. So I'm doing this, taking this level set. So what do I do?
Delta f is equal to lambda delta x.
Exactly. And provided there is this condition, though, the non-vanishing condition that I have to check. So equals lambda times. So what do I get over? 2x, y, z. Okay. So note delta h is non-zero on my set, correct? Because all of those cannot simultaneously be 0. Yeah, because their squares have to add to 9. Okay, so I just solve. So what does this give me? Come on, this is straightforward. I mean, it's a computational exercise. So which one should we look at first? Maybe the easiest to look at the z part, right? So it tells me that 2z is lambda times 2z. So what has to happen? If z is non-zero, then lambda has to equal 1. Can lambda equal 1?
No, then 2x minus 2 can't equal 2x.
Yeah, exactly. So solve this. So 2z equals to lambda z. Z not equal to 0, lambda equal to 1. But then that gives me 2x minus 2 equals 2x, which is not possible. Which is not possible. So therefore, so So we must have z equal to 0, etc. And then you can solve. But maybe we'll just go a little bit further. So if z is equal to 0, then what are the conditions? Then what do I have to solve for? How do I do this? See, a priori, so even before this, just to step back a little bit, how many equations are there to solve for how many unknowns? The Lagrange condition. Yes. Sorry. So the Lagrange condition is giving me something. So the number of things that I have to solve for is 4, right? I have to solve for x, y, z to get the points, the candidate points on this constraint level set, such that the Lagrange condition is satisfied. But there are 4 unknowns. So I have x, y, z, and lambda. But if I equate the coordinates, I'm going to get only 3 equations. So how do I proceed further?
We have a constraint equation also.
Right. So we have 4 equations and 4 unknowns. And in general, this is what is going to happen. So I'll just write this down. So we have to solve x square plus y square equal to 9. And then 2x minus 2 is going to be 2 lambda x. And 2y plus 4 equals.
So why are we assuming equality in the
Right.
constraint?
Because, notice. So this is where we.
Oh, okay, sir.
Right. So okay, so let me just schematically, this is B, and this is the domain is really the union of both of these. And on an open set, I know how to do max min using critical points, etc. And on the boundary, I know how to do this because of Lagrange multipliers.
Okay, sir. Okay.
By the way, so I did not really classify this critical point, whether it's a local maximum or a local minimum, Hessian, etc. Do I need to do this here?
Sir, I have a doubt, sir, in this question.
Yes.
Is it necessary to split it into the interior and the boundary of the ball? Can't we not do it just using one method?
Okay, so what would this method be?
I'm not sure. I mean, can we use the Hessian and all that, the critical points?
You see, okay, so first, if I have a critical point, then by definition, a critical point is where the derivative vanishes, right? But just look at the lower dimensional situation where I'm maximizing a real valued function on a closed interval. And in that case, I really have to treat the boundary separately, right? The function absolutely need not have derivative 0 over there, but it can very well have maxima or minima at that point, at those points, right? So the exact same thing is happening over here. If you remember where we said that, so why is it that at a critical point we said the derivative has to be 0? Because we needed to step in all directions. You should really go and look at the proof of this. Even the one variable proof will give you an idea. And essentially the way we did it for multiple variables is that we use the one variable proof. We just went in all directions.
I understand. I can visualize the one-dimensional case.
Right. So, so the fact that the derivative is 0 really depends on being able to move in all directions. Right. Otherwise, it's not. Okay, but okay. So now what do we have here? So this is 2 times lambda, and now you can. So, for example, from here you can get x and y in terms of lambda. No? So this is just calculation. So what do I get? Lambda equal to Oh, sorry, not lambda. Let's get x and y in terms of lambda. I mean, you can do it in multiple ways, but so what is x equal to here? I cancel 2, so I get 1 divided by 1 minus lambda. Just check, please. That's what I have in my notes. And y equals minus 2 divided by 1 minus lambda. Please check. So anyway, I substitute these values into this equation, solve for lambda, etc. Solve for lambda, and I will solve for lambda. So, okay, might as well do this. So what do I get? 1 minus lambda, the whole square turns out to be, check please, what do I get? So I'll get 1 by 1 minus lambda the whole square. So 5 by 1 minus lambda the whole square equals 9, etc. Right? So get two values of corresponding values of x, y, z, etc. Okay, but remember I had this earlier question. No? So for the critical point, I did not really look at the Hessian at all. Was there any need to do that? Should I have done it?
I think knowing what the value of the function at that point is plus the values that we get over here is enough to classify it.
Right, because we really, I mean, if we really wanted to find out the local behavior as to whether locally it is a maximum or a minimum, then yes, then I should have done that. But just like in the one variable situation, this is a continuous function on a compact set. Maxima or minima have to occur at these points. That's what our theory is telling us. So we simply now calculate a table of values. So look at f of each of 3 candidates and pick largest, smallest values. So that doesn't really change. It is just like the one variable situation. Okay. Okay, so any questions so far? Okay, so let me just say solve more examples, say from that's the book that I referred to, which is really more a recipe-based book. I mean, they tell you the heuristics also, but it's more a recipe-based book. But as compensation, he says it has lots and lots of examples, and it tells the recipes very clearly. So you can use this for practice. There is also a very nice application to economics there. You know, economics uses a lot of calculus. In general, you know, when it comes to applying mathematics in, so these days you talk about data science, machine learning, etc. When it comes down to it, a lot of it is going to be calculus, multivariable calculus, for which then you need linear algebra and some statistics. So these things are really well worth knowing. Yeah, so do look at this application to economics, do some practice problems. You know, there are going to be some problems on this in the final exam, right? Please do not lose those marks because this is straightforward. It's just a matter of knowing the statement and being able to apply it. Okay, so let's now see an example of the implicit function here. So I assigned some problems from Rudin. Let's pick one of these problems and let's work it out. Okay, one more thing. For Lagrange multipliers, there was also the multivariable situation, right? If there was a case of multiple constraints. But even in that case, really the algebra stays the same. Instead of having this equation where the gradient of f is a single lambda times the gradient of h, what you have is that the gradient of f is a linear combination of gradients of the individual linear combination of individual gradients with each one multiplied by a separate lambda. So it just means solving more equations, right? So do some practice of that too. I think there is something like that on the homework. Just check. Does anyone recall? I think I probably did put something like that in the homework. Yes, so there is one problem with two constraints. Okay, so let's now go on to seeing an example of the implicit function here. So this is Rudin 9 point, just see. (9.21). So the function is f of x comma y equals 2x cubed minus 3x squared plus 2y cubed plus 3y squared. Okay, very good. And this was a problem, I think, on the homework. So where you were asked to classify the extrema. But what we want to see is now we want to consider the level set at 0. So S is equal to x comma y such that f of x comma y equal to 0. And you want to find those points where I can locally solve for y in terms of x or for x in terms of y. So what does the implicit function theorem tell us to do?
I think we would want to find partial derivatives with respect to x and y, and we'd need to examine points at which those vanish. So
Correct.
those are candidates for points where we cannot do our
Correct. So where the partial derivatives are not, where the respective partial derivative is not 0, there the implicit function theorem assures me that I can solve locally for what? Okay, so let me write this. Implicit if then near P I can solve for what in terms of what? So this you should know clearly. So think of the linear situation. What this is saying is that if if you have a linear equation, and if you have some columns that are linearly independent, then I can solve for those columns, the variables corresponding to those columns in terms of other variables, or for other variables in terms of those columns. Which one is it?
I think that variable in terms of the other columns.
Right. So, so if you have seen, by the way, was this terminology used, pivot variables and free variables, in your linear algebra course? And when you do row reduction, you get this echelon form, no? No, this was done, or this language was not used?
So we did call the values at which, the columns at which we got one's pivot columns. We did
Correct,
call
exactly.
that.
Exactly. And so you see, when you're solving an equation using this, what does it mean? That in that variable, you get, so that variable, for that variable, the coefficient is 1. And for the other variables, coefficients could be anything. But because the coefficient of that variable is 1, I simply get to solve for that in terms of other variables. Okay. So what is it here? When the derivative with respect to y is non-zero, then that means I can solve for what in terms of what?
Y in terms of x.
And similarly for the other. Okay, so let's just so let's see this. I mean, so this is again just a matter of calculation. No? So and where x in terms of locally. And the point here is that not only can I solve, but the solution has the same level of differentiability as the original function, right? This is sort of the key point. If the original function is C1, the function that I have defined, if it's a C1 function, then this implicit solution of one variable or a set of variables in terms of the other variables is also going to be a C1 function. Okay, so what is the, so which one are we doing in terms of the other? So let's sorry, so so which one shall we do first? Y in terms of x. So let's calculate this. Or let's just have the gradient worked out once and for all. So what is the gradient? This is going to be 6x square minus 6x and 6y square plus 6y. So or let's say equal to 0. It's easier to solve. When y is what? 0 or minus 1. And in that case, what is the value of x? What are the corresponding points? When y is equal to 0, what solutions do I get? Okay, so I'm working out the algebra on the fly. Okay, so please help me over here.
X should be 0 or 1 when y is 0.
Okay, so let's see. When y is 0, then 2x cube minus 3x square is.
Oh no, sorry. No.
Something is. Corresponding points. When y is 0, x is equal to. Okay, so 0, 0, and what 0? So I get 2x minus 3, right? So that means 3 by 2, isn't it? Just check.
Yes, sir. Yeah, that's what I'm getting.
Right, and so when I have minus 1 as the value of y, what are the values of x? Okay, so a bit of algebra over here, right?
So 1 comma minus 1 is a point. I mean, x is equal to 1 is a solution.
Okay, so x is equal to 1, y is equal to minus 1. Is that it? So let's.
I'm not sure about the other. I'm just doing it in my
Okay.
head.
The other one is minus half or minus.
So I'm getting a cubic equation, no, in this case. But it's easy to solve, is it, or what? Oh, okay. Now I remember. There was excuse me. So this is the point is this itself is if I so this is 2 times x cube plus y cube minus 3 times x square minus y square, right? And so the whole thing just so the whole thing is it's easier to, so this is x plus y times some quadratic. And what is that quadratic? So you have to work out. I think I did this somewhere. So 2x square minus 2xy plus 2y square. That's going to be okay, no? That's going to come from the first term. And then from the second one, you are going to have 3x, 3x plus 3y, but with a, sorry, 3x minus 3y, but with a minus sign. So minus 3x plus 3y. And now this is okay, you see, because now it's a question of solving the quadratic. So just check that these answers are okay. So at all other points, we at all other points, y is locally a C1 function of x. But can we say that at these points, y is not locally a C1 function of x?
No.
See, just based on what we have done, we cannot really say that. Okay. So we really have to see what the behavior at this point is. So what happens? So how do we see this? And here, see, what really is going to happen over here is the following. I mean, what we will see is what happens when the points approach these bad points. Okay. But really, geometrically, you can sort of see what is going on over here. What is the graph of this level set? When I plot the graph of this, what is it going to look like? Remember, I have been able to factor this. So the level set is really a union of two sets. One of those is the line y equal to minus, correct? And what about the other one?
I think it's an ellipse.
Correct. So if you think about it, so this is going to be okay. So just looking at the picture, you can dispose of two of these points. Which ones? So I haven't done this, but please check this for yourself. That I think that the line and the ellipse are going to intersect. If that is the case, then the place where the line intersects the ellipse at those 2 points, you see, you cannot really solve for one in terms of the other because there is ambiguity, right? If I have a cross, then near that point, if I give you the value of one variable, I cannot find value of the other variable because there are two different values, right? There are two different branches of this. So there it is not going to work. And at two other points also, it is not going to work. namely the place where you have. So if you okay, so which one are we doing over here? We are trying to solve for y in terms of x. So if I'm trying to solve for y in terms of x, any there is vertical tangent, it's going to be maybe problematic, right? And the way if you see, if you part this part. So which were the solutions that came from the quadratic? Yeah, the solutions that came from the quadratic that did not come from the linear part are 3/2, the 3/2 0, and minus 1/2 minus 1. Now you see what is going to happen at those points is that if I try to solve for y in terms of x, can I do that? Remember, the highlighted part over there is the highlighted part is 0, right? So I can think of that as a quadratic equation and solve for y in terms of x. Let's do that. So um, at any point of S, we have y equal to minus x, or let's write that down, 2y square. So 2 times y square, and so help me over here, plus something times y. So what times y? 3 minus 2x. Sorry, 3. Yeah, 3 minus 2x times y. And then what do I get? Plus 2x square minus 3x. I hope I got that right. Oh, sorry, 1 second. And I'm getting confused over here. In terms of x, yeah, okay. So what does this tell me? This tells me that y is equal to, I can just use the quadratic formula, right? So this is going to be 2x minus 3 plus or minus. So this plus or minus whatever, right? Divided by 4. And then I get to write the discriminant over here. Discriminant. So the way to do this is to really see what is happening at so at the 4 potentially problematic points, we have to examine local behavior. And See, the idea is going to be something like this. Okay, because I really should have worked this out beforehand. I thought I was going to do it on my feet, but it's something of this nature, right? So if we have something like this, then near this point and near this point, I'm going to get two values if I step off. And even over here, if I take a slightly different value of x, notice what happens. If I take a slightly different value of x, I'm going to get the plus or minus sign in the discriminant is going to come into play. So again, I'm going to have two solutions. Right? So in this particular case, it is not going to work anyway. So check that. At each of 4 points, y cannot be expressed uniquely in terms of x. And then carry out similar analysis. For x in terms of y. So what is this going to involve? This is going to involve looking at the other partial derivative and seeing where that is non-zero. But just looking at the picture, can you tell me which points are now going to come into play? How many points are there where there is potentially a problem? Think of this geometrically, okay, not in terms of calculations.
There'll be 4, I think. The same
And
two
will it be,
intersections.
and will it be the same 4 points?
No, 2 of them will be the same. The intersection of the line and the ellipse are still problems. And the other 2 are, I guess, the top and the bottom of the ellipse.
Right. So where the tangent line is going to be horizontal. So those are going to be the other points. So you should do the calculations and check that this is indeed the case. So check the units. There will again be 4 bad points. Okay. Yeah, so I really do not have anything more planned for today. We can go through some of these details if you want, but otherwise I would just like to stop and ask you whether you have something that you would like me to do.
Sir?
Yes.
Sir, last week I'd asked a question about the inverse function theorem and whether we can say anything more in terms of the Hessian. I realize that my question doesn't quite make sense as I stated it, because I had asked if we can do something with functions from Rn to R, which the inverse function theorem doesn't apply for. But I think we can make a slightly different statement. I think for the implicit function theorem, we should, for a function from Rn to R, we should be able to say that no, I need to say it properly. I guess, sir, what I'm trying to say is that here our points are failing to be expressed uniquely in terms of the other variable, because the graph is curving in on itself. So if, like, what I want to say is that if these points are local maxima or minima or even saddle points of some function, then that is a sufficient condition for a point not being able to be expressed in this way.
Okay, so as I understand, you want to give some, okay. So the implicit function theorem tells me a sufficient condition to be able to solve locally. What you are trying to do is to give some condition that is also necessary.
Yes, sir.
That is to give a guarantee that in this case, actually, there will definitely be failure. Is that what you're trying to do?
Yes, sir. Yeah.
Not clear to me. Clear to me, I think. But one, so sorry to change this a bit, but I do want to sort of let me say this. Implicit theorem is me in showing level sets of functions are manifolds. Under the okay, let me not say not always, okay. That is when the okay. This level sets of when the derivative of the function in question satisfies the requisite non-vanishing condition. So the requisite non-vanishing condition, remember what that means. That means that sufficiently many columns of this must be linearly independent. So that this must be a full rank. The derivative as a linear map must be a full rank function. If that is the condition that is met everywhere on the level set, then you see that around every point I can get a neighborhood which locally looks like just an open set of Rn, which is what makes something into a manifold. So at some point, if you like, this is really definitely worth understanding. Okay. And the implicit function theorem tells you that it is also giving you the necessary smoothness condition, right? So the function that the implicit function theorem gives you, or the sets that the implicit function theorem gives you, those are like those can be used to give charts. Okay, that's in terms of the definition of a manifold. So this is worth learning at some point. Yeah. So in the remaining in the remaining part of the week, I don't really want to subject you to anything. If you want me to solve some problems or do something specific, so I would rather not discuss anything new, okay, because your final exams week is coming up. So to pile something on more is, I think it is not appropriate at this time. But if you want me to solve some problems or answer some questions, then please send them beforehand to me, because I would like, it's likely that I would need to think about it. I may not be able to answer on the spot. So please email me, and what I will do is, in the remaining 2 class times, I will be available. And if there is more than 1 or 2 people, then we can even have a session. but otherwise, I think I have sort of tortured you enough. And so officially we will stop today. But I will be around in the remaining two class times to answer any questions.
Recording stopped.
Yeah, so are we ready to call it a day? Or is there anything else?
So in the implicit function theorem, if the dimension of the image is greater than the dimension of the domain, then can we say something?
No, the dimension of what?
If
If the dimension of the codomain is greater. Right.
Yeah, it's greater.
So, but you see, I mean, the sort of silly answer to that question is that in that case, the implicit function theorem is not applicable because I want surjectivity, right?
Okay, sir.
Right. No, but I mean, it's a valid question in the sense that I should still be able to.
Like I wanted to.
I should still be able to say something about what
level
kind,
sets,
something about level sets. And this rank theorem tells me that I can do something. I can have some kind of standard form. But it's a bit more complicated. And you see, there should be something symmetric, right? In the same, like the following. Suppose I have a function that goes from a smaller dimensional, smaller Euclidean space to a larger dimensional Euclidean space. And let us suppose that the derivative is an injective function. Right? In that case, can I somehow say something? Yeah, and in differential geometry, you will see, I think this is called local immersion, basically. I mean, the details are important, but you should also keep the big picture in mind. What these theorems are designed to do is that they allow you to really practice, put into practice this thinking that locally calculus is linear algebra. That's the idea behind these things. This does not come so much into fore when you're doing one variable calculus, because there is just the tangent line. I mean, what else is there to say? But in many variables, I mean, linear algebra itself is a thing, no? So, yeah, okay. So again, for this coming quiz, expect something similar in that I will ask you for some justifications here and there. But really, it will be computational. So you should know the recipes properly. And I've even told you. So just like for yesterday's quiz, I told you which three theorems you should know thoroughly. So even for the coming one, I have told you. I mean, it's going to be this Lagrange multiplier method, exactly how it works, and the inverse and the implicit function theorem. So there is enough practice on the homework to do this, to do calculations and see what is going on. So please work everything out properly, and you should be fine.
Thank you, sir.
All right. So thanks everyone for bearing with me as I was learning this material myself. So hopefully I didn't make too many mistakes. Yeah. So thanks everyone. And by the way, I will be there. I should be there in CMI on the day before our exam. So our exam is on the 22nd. I should be there on all of 21st. So if you want to drop by and ask any questions, your exam on the 21st, is it in the morning or afternoon?
In the morning.
Okay. So that means once you are done with that exam, you should be free the rest of the day. If you want to just drop by, ask any questions, I'll be happy to chat with anybody. Okay.
Thank you very
Thank
much for the course, sir.
All right. Okay. Thanks everyone. Bye.
Thank you, sir.
Thank you, sir.
And see you.
Thank you, sir.
Thank you.